Good morning, this is Engineering Statics. Once again, we're working off the Hibbeler text, 5th edition. And we're working through chapter 4. We're doing equilibrium analysis. And we're working on our free body diagrams. We've worked in 2D. We'll say support reactions. This is table 4.1 for our free body diagram support for support reactions in 2 dimensions. This is page 160 to 161 in text. And for 3D, we looked at table 4-2. This is page 186 through 187. Okay, so let's get back into the thick of things. Let's power through some problems in both 2D and 3D, and we'll move on to some new stuff involving friction analysis. So let's start with the problem. Let's look at problem 4-4 on page 179. And it says determine the reactions at the supports. This is a 2-dimensional problem. So we know we need table 4-1. Point A, if we go by the table, so point A is basically a roller, which means it's free to move in the X direction, but not free to move in the Y direction as is supported there. So the support reaction can be modeled as a Y direction force. B is a pin. So it prevents movement in both Y and X direction. All right, so the first thing we do, we always start with our free body diagram. Also, we notice we have a distributed loading. It's an irregular shape, but we can clearly model it as the combination of a rectangle and a triangle. So let's get to work. Show the beam. We said A is a roller. We'll model that as normal force, which says normal is perpendicular. Beam, the pin at B. Both X and Y components. Then the loading, so we said in our previous work that to represent the resultant force from a distributed loading is pretty much the area. Use the area formula. So for the rectangular, the load and intensity 600 Newton per meter. And for the triangular, is the difference of 900 Newton meters and the 600 Newton meters. So that gives the intensity here 300 Newtons per meter. The resultant force for the rectangular acts in the centroid, and for rectangular is right in the middle. So the resultant force here is the area, which would be the length. So we have 3 meters, 3 meters. So it's a total length of 6 meters. So 6 meters times 600 newtons per meter. And for the triangle, I'll come over here, the area is half the base, and this is from Appendix B, half the base times the intensity, 300 newtons per meter. And that acts, we said, a third from the base, so it acts in this, which a third of 1 meter, this will be 1 meter. It's where that resultant force of the triangular loading acts. So now we have everything to get to work. And the question wants us to solve for the reaction at the support. So the NA, BY, and BX. We have 3 unknowns. So we said we always start to remove as many unknowns as we can. So we take the moment about point B and set it equals 0, which is our requirement for equilibrium. That immediately eliminates BY and BX because they act at point B and therefore do not cause a moment about point B. Okay, so with that being said, we have the resultant force from the rectangular loading. So that's the 6 meters times 600 newtons per meter. It's counterclockwise about point B, so it's positive. The perpendicular distance is 3 meters, plus the resultant force from the triangular loading. Once again, this is counterclockwise rotation, so positive. And it is, the perpendicular distance is the 3 meters plus the 2 meters to point B. So it's 5 meters. Then we have our unknown, the NA, which acts in a clockwise, causes a clockwise rotation about point B, so it's negative. And the perpendicular distance here is 6 meters. Solve for NA. (2,175 newtons). Let's go to a clean page. If we take our forces in the x direction, set it equal to 0 for equilibrium, we only have the Bx that acts in the x direction. There are no more x direction forces. So Bx equals 0. Last but not least, we're solving for By. If we sum our forces in the y direction equal to 0, requirement for equilibrium, we have the By plus the Na, which we solve for, minus the 2 resultant forces from the loadings. So minus the 1/2 times 3 meters times 300 Newton meters, minus the 6 meters times the 600 Newton per meter. Set it equals 0. So we took care of our y component here, y direction force here, y direction force here, and the y direction force here, leaving us to By 1875 newtons. So we solve for the reactions at the supporters. Let's take a look at another problem. Four -8 on page 180. Here the problem says they give us the dimensions of a jib crane. The mass is 800 kilograms. Well, we're dealing with forces, so we have to convert mass to force. Force is mass times acceleration. Weight is the force in this question, so it's mass times acceleration due to gravity. So it'll be 800 kilograms times 9.81 meters per second squared. That gives you 7848 newtons. All right. Next, the problem says the center of mass is located at G. So that is where that weight is applied. They give you F is 15 kilonewtons, which is the weight hanging off the hook there. The bearing at A only has a horizontal force, and the bearing at B has both horizontal and vertical components. So those are our two support reactions. So let's draw a free body diagram. We have the force F here. The weight is located at G. G is 0.75 meters from the end. So this distance here, which leaves this distance here to be 2.25. And this weight here is 7848 newtons, as we just calculated. Point A, right here, it said only a horizontal component, while point B has a horizontal and a vertical component. This is given in the problem statement. And I think that's all we need. The height here is 2 meters. I believe I have everything we need. Okay. So we have two unknowns at B. Let's get rid of that first. So we take the moments about B, set it to equal 0, condition for equilibrium. AX causes a positive counterclockwise rotation about B. The 7848 Newton force and the 15 kilonewton force both cause clockwise rotation, so negative. So the perpendicular distance, AX times 2 meters, that's the perpendicular distance from AX to point B, minus the 7848 newtons times the perpendicular distance, which is 0.75 meters, all in respect to point B, minus the 15,000 newtons, kilonewtons, 1,000, times the perpendicular distance is 3 meters. Set it equal to 0, solve for AX. .4 kilonewtons. Therefore, take our sum of forces in the x direction, set it equals 0. You have bx minus ax, which is 25.4, equals 0. There are no other forces in the x direction, therefore bx equals to 25.4 kilonewtons. Last but not least, take your sum of forces in the y direction. You have the last unknown, by, minus the 48 newtons, minus the 15,000 newtons, equals 0. By gives you 22.8 kilonewtons. Let's take a look at another problem. (419), page 182. So we have a cantilevered footing is used to support a wall at point A. Okay. Determine the uniform distribution loads. So this way we're going backwards. They're giving us the resultant force or the force loadings, and they want us to determine the distributed loadings at WA, WB at points A and B. And the wall forces are 8,000 pounds, 20,000 pounds. So let's draw a free body diagram. Always start with a free body diagram. So we have the loading at B. Loading at A. This thickness is 2 feet. This thickness is 3 feet. Well, I should say width is 3 feet. It's 8 feet between them. We have the 8,000 pound force here and the 20,000 pound force here. Okay. Okay. So if we take the moment, I should say some of the moments about point A, set it equals 0, static equilibrium. The 8,000 pound force creates a clockwise positive rotation about point A. we didn't know. So it's, I think, point B here, point A. We left off some information. Okay, so the 8,000 pound force creates a clockwise, so that's negative 8,000 pound force, perpendicular distance from point B to point A. We have 1.5 feet plus 8 feet plus the 1 foot. So that gives you 10.5 feet. WB, so remember that's a loading we're solving for that caused and is pushing up, so causing a counterclockwise positive rotation about point A. So the loading is the area which results, what gives us the resultant force. So it'll be the loading WB times the width, 3 feet, which will give us the area there. Then the perpendicular distance once again, because WB acts right in the middle, centroid of the rectangle. Perpendicular distance once again is 10.5 feet to point A. And the 20,000 pound force, which is 0.25 from the edge, that creates a positive counterclockwise rotation. So that's 20,000 pound force. And the perpendicular distance there is 0.75 feet. 1 foot minus 0.25 feet gives you 0. Solving for the loading, remember the units, this is an intensity. So then for the distributed loading at point A, the last unknown, some of the forces in the y direction, the loading at B, the resultant force in the y direction is the area, right? So it's the 21 point, this is pound force per feet, times the width, 3 feet. That gives us the resultant force of the loading at B, minus the 8,000 pound force, minus the 20,000 pound force, plus the loading at A times the width there, which is 2 feet. One unknown, solving for the loading at A, you get 10,700 pound force per foot. Okay, let's do some three-dimensional work. Let's look at problem 4-28. It says determine the components of reaction at the fixed support at A. And they gave you the forces, 400 Newton, 500 Newton, and 600 Newtons are each parallel to the X, Y, and Z axes respectively. So the fixed support at A, go into our table 4.2, page 186 and 187, fixed support. So a fixed support has in 3D, you have your Fx, Fy, Fz, and your moments. So the fixed support resists translation in all 3 directions, and it resists rotation about all 3 axes. So, as always, let's start with our free body diagram. Bear with me. So we have our y-axis. We have our x-axis. So negative x direction, x-axis. And we have our z-axis. So we have one force in each direction. So if our 400 Newton force sense is in the negative x direction, then to balance that out for equilibrium, our AX has to be, the sense has to be in the positive x direction. Likewise, for the y force, 500, that's in the positive y direction. So our AY has to be in the negative, the sense has to be in the negative y direction. The z force is in the negative z direction, the sense that is. So the has to be in the positive. And then our moments, remember counterclockwise is positive. So we have our 6 unknowns. 3 force components, 3 moments. All right, let's get to work. So sum of our forces in the x direction equal to 0 for equilibrium. We have AX minus 400 newtons equals 0. AX equals 400 newtons. Sum of our forces in the y direction equals 0. Set it to 0. You have your AY, you have your 500 Newton minus your AY equals 0. So AY is 500 newtons. So for your Z, sum of forces in your Z direction, set that equal to 0. You have your AZ minus your 600 Newton force equals 0. AZ is 600 newtons. So we have eliminated 3 unknowns right there. Now we have to work the moments. So some of the moments about the x-axis so we have to start with what's given. Let's take a picture of this when we get to the next page. Okay, so the sum of our moments about the x-axis, we start with our MA sub x, which is due to the fixed support. We have to have that. All right, the 500 Newton y direction force causes a clockwise, so negative rotation clockwise, which is negative value about the x-axis. So we minus that. And the perpendicular distance from the 500 Newton force to the x-axis is the 0.75 meters plus the 0.5 meters, which gives you 1.25 meters. The 400 Newton force is parallel to the x-axis, so it does not cause a moment about the x-axis. The 600 Newton force causes, once again, a clockwise rotation about the x-axis. The perpendicular distance there from the x-axis is 1 meter. Solve for the max. You get 1225 Newton meters. Let's go to a fresh page. Bring our drawing back over here. So then sum of my forces about the y-axis, set that equal to 0. Once again, due to the fixed support, you have a moment about the y-axis due to the fixed support, MAY. The 400 Newton force causes a clockwise, so negative rotation about the y-axis. The perpendicular distance there is 0.75 meters. The 500 Newton force is parallel to the y-axis, therefore it does not cause a moment about the y-axis. So the 600 Newton force causes a clockwise, so negative rotation. I'm sorry, negative value about the y-axis. So the perpendicular distance from the 600 Newton force to the y-axis is 0.75 meters. Solve for the MA sub y. You get last but not least, some of my moments about the z-axis. The 400 Newton force, there is no perpendicular distance from that to the z-axis. The 500 Newton force line of action runs to the z-axis as well. And the 600 Newton force is parallel to the z-axis, so that does not cause a moment about the z-axis. So therefore, we have solved for our 6 components of the support reactions. Let's do another one in 3D. .431. Here we have a concrete slab. Once again, they gave us mass. Then the weight is mass times acceleration due to gravity. (2,400 kilograms times 9.81 meters per second squared. You get about 23,544 newtons. Okay. This slab is rectangular. It's a 3-dimensional problem. So the weight acts in the center of gravity. Let's draw a free body diagram. This is our z-axis, y-axis, x-axis. The problem, we have a TA here. This is 2 meters. And you have a TB in the Z direction here. You have a TC here in the Z direction. And you have a 15 kilonewton force here. This is 0.5 meters. This is 1 meter. 1 meter. And this is 2 meters. So this is a rectangular 4 meters by 2.5 meters. So the center of gravity here, let's go over here. So this is where the 23,544 Newton force X. And that's basically 1.25 meters in the width and 2 meters in the length direction. That would be the coordinates of where it acts. I believe we have everything we need. And the question says, determine the tension in each of the cables. So that's TA, TB, TC. Okay. So if I take the moments about the x-axis, then we can eliminate TB and TA because they lie on the x-axis and therefore do not cause a rotation about the x-axis. However, TC does, and TC causes a positive counterclockwise rotation about the x-axis. So TC times the perpendicular distance, which is 2.5 meters, minus the 15,000 Newton, minus the 15,000 Newton force, which causes a clockwise rotation, negative. Perpendicular distance there is 0.5 meters about the x-axis, minus the weight, and the perpendicular distance there, we said from the x-axis, is 1.25 meters. Set that to equal 0. TC is 14 newtons. Let's go to a clean page so we can continue working. All right, so we solve for TC. Let's take the moments about the y-axis. This eliminates TA because TA is on the y-axis and allows us then to solve for the TB, since we already now know TC. So TB causes a clockwise. TB causes a clockwise rotation about the y-axis, and the perpendicular distance is 2 meters. The 15,000 Newton force causes a counterclockwise. The weight causes a counterclockwise, and the TC causes a clockwise. So let's go. We have the weight. Perpendicular distance is 2 meters to the y-axis, plus the 15,000 Newton force. Perpendicular distance is 3 meters, minus TB. Perpendicular distance is 2 meters, and minus the TC, which we already know now, which we calculated to be 14,772 newtons, times the 4 meters. Solve for that. TB is 16,500 newtons. There's one unknown left. So we take the sum of our forces in the z direction, set it equals 0. You have your TA minus your TB minus your TC, plus your TC. I'm sorry, your TA plus your TB, plus your TC, which is 14,000, minus the weight, which we said is 23, and minus your 15,000 newtons. Solve for TA, you get 7,272 newtons. Let's go into some new stuff. I'm going to talk about friction. Friction is a force that resists movement between two contacting surfaces. And here we're talking more about dry friction. And we mean dry friction occurs between the contacting surfaces of bodies when there is no lubricating fluid. So to represent this, let's consider the effects of pulling horizontally on a block of weight, and we'll just call that weight W, was resting on a rough surface. So let's go over some terms. We said W is the weight. We have an applied force P that's trying to move the block, or say cause the block to slide, and is dragging it to the right. So then the floor exerts a normal force. Remember, normal means perpendicular to the surface. And also a frictional force, F sub S. Frictional force exerted by a floor. The normal force acts a distance x away from the line of action of the weight W. And this is related to the tipping, to prevent the block from tipping. So we'll say tipping effect. So as the pulling force, P, as it is increased, the frictional force correspondingly increases until it attains a maximum value, we'll say Fs. When this value is reached, any further increase in the pulling force, P, will cause the block to move. So the frictional force, Fs, is proportional to the normal force and related to by the constant of proportionality, mu sub s. And this mu sub s is the coefficient of static friction. And as you see, the normal force and the static friction force create a resultant force. And the angle between the resultant force, phi, and the normal force is called the angle of static friction. If you've seen these equations before, it's just different variables, different terminology, different uses. But the equations and the logic is the same as what we learned in chapter 2. And I'm on page 200 through 201 in the text. Also page 201, and see table 4-3 for values for mu sub s for certain materials and surfaces, I should say. So once that pulling force P is increased so that it is greater than the frictional force, F sub s, the frictional force reduces to a lower value, we'll say F sub k, which is called the kinetic frictional force. Kinetic means movement. Therefore, the block will then begin to slide with increasing speed. The kinetic force, once again, is related to the normal force by mu sub k, which is the coefficient of kinetic friction. Typical values of mu sub k are approximately 25% lower than the mu sub s values from table 4-3. So let's look at example problem. .12 on page 208. Here we have a crate has a mass of 20 kilograms. If a pushing force of 80 newtons is applied to the crate as shown, determine if it remains in equilibrium. And they gave us the coefficient of static friction from the crate and the floor. So let's get to work. Always start with your free body diagram. Pushing force, this angle here is 30 degrees. Width of the box, 0.8 meters. This is applied 0.2 meters from the floor. The weight is the 20 kilogram mass times the 9.8 meters per second squared. Since this is a rectangle, it's applied in the centroid, the center of it. This is all right. We have a frictional force. Is the pushing force is pushing it to the right, so the frictional force is resisting movement, so it's opposite in direction to the force. We have a normal force, where we said the line of action to prevent tipping is somewhere off the line of action of the weight. So our normal force. So we have two unknowns. Well, actually three, because they want us to solve for where the normal force acts. X, we just said, is the distance away from the, say, center of gravity that the normal force acts to prevent tipping by the pushing or pulling force. And that's distance x. So doing out some of our forces in the x direction, the x direction component of the 80 kilonewton force, the 80 Newton force is cosine. Minus some of our forces in the y direction, have your normal force minus the weight of the crate minus the sine of the 80 Newton force your normal force is so now if we take the moment about point O, to determine where the normal force operates, both the X and the Y component of the 80 Newton pushing force create a moment about point O. The horizontal component creates a clockwise negative. The vertical component creates a counterclockwise rotation positive. The point O is along the center of gravity or the center line. So the weight does not cause a moment about O, but the normal force does. And if we assume it operates to the right of the point O, then it will create a counterclockwise positive. And we calculate that normal force to be times some distance x. Solve for x. .08 millimeters. That came out to be negative. So instead of normal force operating to the right of the center line, it actually operates to the left to the center line. So we should have had it over here. Additionally, the maximum frictional force developed at the surface of contact is mu sub s times the normal force. Mu sub s was given at 0.3. Normal force we calculated 236.2 newtons. This comes out to be 70.9 newtons, which is greater than the frictional force we calculated of 69.3. Therefore, the pushing force is not enough to cause the crate to move. Let's take a look at the problem. .443, page 214.